All right, everybody. So I'm going to do the derivative of the natural log function today. I'm going to do it slightly differently than JM did it. He used a different proof, which you saw in class, so I'm going to show you another way to think about it. I think in an earlier video I talked about the natural log function is defined as the integral from 1 to x of the graph, or of the function 1 over t, which means here's the graph of 1 over t, this decreasing function here, vertical asymptote, horizontal asymptote. The natural log is defined as this area under that curve from 1 to x, and x moves, okay? So if we say, okay, our function f of x is equal to the natural log, which is the area under the curve, or the integral from 1 to x of 1 over t, and then I say, well, what's the derivative of f of x? Okay, so the derivative of the natural log, if you remember from the second fundamental theorem of calculus, when you're integrating when you're deriving an integral, they essentially cancel each other out, and this variable gets plugged into there. So the derivative of the natural log function is just 1 over x. Now, you also have to remember that if our function f of x had a composite function in it, so in other words, this is 1 to u of 1 over t dt, and I ask the same question, the derivative. So the derivative of the natural log with respect to x is 1 over u times, then you have to use chain rule and do the derivative of that upper bound, which we'll call u primed. So the two formulas that you will use are the derivative natural log of u is u primed over u, and the derivative of the natural log of x is 1 over x. They are essentially the same formula, because in this one here, x goes to the denominator, that's our u. The derivative of x is just 1. So it's the same thing. All right, so do a few examples, and then I'll give you some practice questions. So if I ask for the derivative of the natural log of 2x, well, 1 over 2x times, what's the derivative of 2x with respect to x? It's 2. So I get 2 over 2x, which is just 1 over x. Another way to think about that is, if you remember your log rules, if you're multiplying the arguments, you can separate them into natural log of 2 plus natural log of x. And so if I'm doing the derivative of that, d dx of all of this is a constant. The derivative of any constant is 0. So then I just look at this, derivative of natural log of x is 1 over x. All right. We will use this technique of breaking stuff up when we get to more complex things. All right. Number 2. The derivative natural log of x squared plus 1. Okay, whatever's in the brackets goes in the denominator, and then the derivative of that goes in the numerator. The derivative of x squared plus 1 is 2x. What about the derivative of x times the natural log of x? Okay, this is actually a product rule question because we're multiplying two functions together. So product rule says the derivative of the first function, which is 1, times the second function, plus the derivative of the second function, natural log of x, which is 1 over x, times the first function. So I end up with the natural log of x plus those two x's cancel, and I get 1. The derivative of natural log of x to the power of 3. All right, another chain rule. Start with the outside function. Drop the 3 down. Take 1 away. Times the inside derivative. What's the derivative of natural log of x? It's 1 over x. So you end up with 3 natural log of x whole squared over x. Or the way you can represent this is 3 natural log with the squared on the natural log. That means the same thing times x. What if you have an exponent on your argument, such as that? Well, your log, there's 2 ways to do this. One is we can follow u primed over u. So the derivative of 3x squared, or of x cubed, is 3x squared. And then the x cubed goes in the denominator. And then you simplify that. That cancels that. And you're left with 3 over x. The other way you can think about it is our log rules allow us to drop the exponent on the argument down. And then it's just what's the derivative of natural log of x? That's 1 over x. And that's the same as that. Okay, now, knowing your log rules allows you to solve more complex derivatives. So if I have, I'm asking for the derivative of the root of x plus 1. First of all, we don't like roots, so we rewrite it as an exponent. Then we use our log rules to drop the 1/2 down. Whoops, sorry. So it's the derivative 1/2 natural log of x plus 1. The 1/2 is a constant, so it just stays. Derivative of x plus 1. Put the x plus 1 in the bottom, and the derivative of that goes up top, which is just 1. So it's 1 over 2 times x plus 1. All right, now, here's the real value in logs. I know nobody really likes logs, but they have value. So if I have this function times x squared plus 1 squared over 2x cubed minus 1. Okay, that looks like a gong show. All right, and if you're going to use the u primed over u, this whole thing would go in the denominator, and then the u prime is going to be a product rule with a quotient rule, and there's a chain rule with that too. That's going to be a nightmare. But logs allows us to rewrite this. So first of all, if you're multiplying arguments, that means you're adding the argument, the logs of those arguments. And if you're subtracting, or if you're dividing, that means you're subtracting. So this expands to natural log of x plus natural log of x squared plus 1 to the power of 2 minus the natural log, and I'm going to write the square root as a power, 2x cubed minus 1 to the power of a half. Then I use our log rules to drop down the exponents. So I get the natural log of x plus 2 natural log x squared plus 1 minus 1/2 natural log 2x cubed minus 1. And now you can do the derivative. This is all equal to f of x. I'm just rewriting it using our log rules. So then f prime of x, you just do each one separately. The first one, natural log of x, is just 1 over x. The second one, 2 is a constant. X squared plus 1 goes in the denominator. The top is the derivative of that, which is 2x minus 1/2. In the denominator goes 2x cubed minus 1. In the numerator goes the derivative of that, which is 6x squared. So I'll just clean it up a bit. 1 over x plus 4x over x squared plus 1 minus that turns that into a 3. 3x squared over 2x cubed minus 1. And you could find a common denominator and put it together, but we'll just leave it like that. Okay, so if you have a log expression and it looks like a bit of a gong show, you can then allow it to expand and then solve it. All right, practice questions for this stuff. Page 325, numbers 41 to 61 odd. Enjoy, people.